Thank you very much, and thank all the organizers, but particularly Elizabeth, for the invitation to talk to this conference. And this is a talk based on work with Hein Nguyen and Guofang Wei, and a continuation of work with a larger number of collaborators. And I've been talking about this problem for a little while, so I was trying to find some new aspects of it to make a sort of a closure. And nonetheless, let me start with the general statement of the problem. So if you have a Riemannian manifold with a metric G, you can think of G through its coordinates Gij of the metric. This forms a positive definite matrix, and the determinant of G is positive. And G upper ij is going to be the inverse matrix of Gij. And so with the help of these coordinates, you can define the Laplace-Beltrami operator on any Riemannian manifold in local coordinates. And this reduces to the usual Laplacian when the matrix is the identity matrix. And so you can define this eigenvalue problem, find lambda such that Laplace of u plus lambda u is 0, and to each non-zero lambda will correspond an eigenfunction on a non-zero eigenfunction. This particular problem is with a Dirichlet boundary condition. So the eigenfunction is required to be 0 on the boundary. And no matter what the manifold is, as long as the domain is connected, compact, and with piecewise C infinity smooth boundary, you will have that you have a spectrum, a sequence of eigenvalues that's discrete, that goes off to infinity. And the first one is a simple positive eigenvalue, and then being simple, the second one follows at some distance. And the fundamental gap is, by definition, the distance between the first two eigenvalues. The eigenvalue, one of the eigenvalues, well, not of this problem, but one eigenvalue came up in the first talk of this conference, in the talk of Emmanuel, and it was lambda 2. I want to point out that in this case, what you have, it's a different boundary condition. You have a Neumann boundary condition, and in that case, so what that is, it's the normal of u at the boundary. The normal derivative of u at the boundary is 0, and with this, the first eigenvalue is actually 0. The second eigenvalue is the first strictly positive one, and you still have a fundamental gap. There is still a definition, and that will be just the first non-zero eigenvalue. Because the first one is 0. So there are some similarities, and in a way you will recognize some bounds that appeared also in Emmanuel's talk, like pi square over d squared and so on, but the problem is different than that one. So this is really a Dirichlet boundary value problem. And again, there are connections between the two sets of eigenvalues, and one can infer some comparison between the two of them, but I will not touch on that on the other problem. So let's talk a little bit about the upper bound on this. So the question is, what can one say about the upper or lower bound of the fundamental gap in general for domains on manifolds, or maybe restricting the manifolds to some special ones, or restricting the domains to some special ones. And a first conjecture was stated independently by Payne-Polya and Weinberger, in about 55, 56 different papers that said that on manifolds with constant sectional curvature K and simply connected, for any bounded domain, if one fixes the first eigenvalue to be equal with the eigenvalue of a ball, then the fundamental gap is bounded above from the fundamental gap of that ball. So this is what I said, what I called recently an isoperimetric inequality, because first of all, it requires some normalization, that the first eigenvalue is the same for both the domain and the ball, but also because I really see it as an isoperimetric problem, because in this case, the convexity of the domain is not even needed. For any bounded domain, you have such an inequality. And this was proved successively, first in Rn, and then on the sphere, and then in the hyperbolic case for sectional curvature -1. So this being the case I'm talking about today. And so let's look now at the lower bound. For the lower bound, the conjecture was just for convex domains. But a little bit more general for the Laplace operator with, for the Schrödinger operator, the Laplace operator plus positive or non-negative convex potential. And again, was conjectured by different people at about the same time, that it's lower bounded by 3 pi square over d square, where d is the diameter of the domain. And I want to make a comment about this because this was for Rn, and why this d squared, and the best way to see it, and then because then I would like to bring this the same question to manifolds. I want to say that for any eigenvalue, any k eigenvalue of the Laplace operator, including the potential or not, in Rn, if one takes a scaling of the domain omega, then this is equal with the eigenvalue of omega times or divided by 1 over t squared. So this quantity, d squared times the fundamental gap, it's actually scaling invariant. So in some sense, it's like a reverse isoperimetric inequality as well, because it's scaling invariant. This time there is no normalization, but because the d squared times the fundamental gap is independent of the size. And one sees this inequality, this equality, the scaling quite easily, because if one looks at the well, let's put lambda1 so it's a little bit easier. The definition of lambda1 as the infimum after all positive functions, let's say you with the property that they minimize the Rayleigh quotient, which is the norm of the L2 norm of the gradient of u dx over omega over the L2 norm of a function. Over omega, then if you take a scaling of the domain, so if you take now t omega, you will realize that if u of x was the function that was the first eigenvalue, or u1 of x is the first eigenvalue of the domain omega, of the Laplace on the domain omega with the boundary Dirichlet boundary condition, then u1 over x over t will be the eigenvalue of the scaling, and then so from the numerator you easily see this factor of 1 over t squared that comes out. Okay, so so this was the conjecture, and it was conjectured simultaneously with a lower bound, that this is when the potential is 0 and the domain is degenerating into a thin rectangular box. And then it was proved relatively recently by Andrews Clutterbuck with previous partial results. So what those previous partial results were about different bounds. So this Zinger, Wang, Yao, Yao paper has a p squared over 4d squared using the Li-Yao gradient method, and then independently Yu Zhong and Ling, Ling being a student of Yao, they improved it to pi squared over d squared with different methods. Well, it's improving on the Li-Yao gradient method, but slightly different approaches. And in fact, I might actually say a word about Ling's approach, because it's in a particular case becoming very simplistic for my own problem. And then Yao also had some other improvement. In the end, let's see what is okay, so I said here that where is it, that the fundamental gap, I think my writing disappears. Okay, so the fundamental gap is a scaling invariant with respect to so d squared times the fundamental gap is scaling invariant. And so when one moves to manifolds, it's natural to wonder whether the d squared is the right power or the right function of the diameter to consider. But if you zoom close enough to a manifold, you can think that locally it's like Rn. So it was natural to try first this d squared as well on other manifolds, and following the same ideas of proving the fundamental gap in Rn. A group of group of people that collaborated in different subsets proved that the same fundamental gap estimate is true for convex domains on the sphere. So for a manifold with constant sectional curvature +1, and the same degenerating bound. So when the domain degenerates to, in fact, it degenerates to a segment, a geodesic segment. And therefore, it was natural to ask what happens for convex domains in Hn, because the Payne-Polya-Weinberger conjecture was proved for all manifolds or all spaces of constant sectional curvature. And already we have two instances, zero sectional curvature and +1 positive, +1 sectional curvature, where the fundamental gap conjecture also holds as well. So therefore, what about the convex domains in Hn? And so far, convexity, by the way, it's meant in the sense of geodesic convexity. Any 2 points in a domain are joined by a geodesic segment that's also included in the domain. And I talked about this before, so I will only state it. It's a theorem that was proved with Burny, Clutterbach, Nguyen, Wei, and Wheeler, that in fact in the hyperbolic space for convex, geodesic convex domains, there is no fundamental gap. For any epsilon and any diameter, you can find a convex domain in Hn that has that diameter and for which the fundamental gap is sufficiently small. And so, okay, so that kind of ruined a little bit the enthusiasm. And so we went back and we said, well, okay, so what exactly was essential in the Euclidean case and in the spherical case, and what can we replicate, and what can we see about the hyperbolic space in opposition to those other spaces? And for both Rn and Sn, the law concavity of the first eigenfunction of any convex domain plays the important role. And in fact, by the way, the law concavity was used in all proofs, even for the milder bounds or the weaker bounds, and including at the end the final proof of the fundamental gap conjecture in Rn, but with different tools. So basically, you want to get quite fine estimates on how law concave U1 was. But in fact, the law concavity of U1 was first proved by Braskamp and Limbin in 2 papers, 75 and 76. One was kind of hard to find. It appears in a proceedings of a conference. And however, when I looked at them, it was very interesting, because these are the kind of papers that are very likely known to exactly this community and less known to the PD community. So one was on extension of the Brun-Minkowski and Prekopa-Leinler theorems, including inequalities for law concave functions, and with applications to the diffusion equation, to the solution to the diffusion equation. And that's exactly what they were doing. They were proving the law concavity of the kernel of the heat equation. And then the second paper that was harder to find was some inequalities for Gaussian measures and the long range order of the one-dimensional plasma. So obviously that law concavity, although was known to the PD people, was less used as such. And in fact, the proof it's not as direct as one would wish. And so immediately in the first paper of Zinger, Wang, Yao, and Yao, where they showed the lower bound pi square over 4d square, they gave a different proof. And same in Ling and Yu Zhang. Or basically, it's not necessarily a new proof, but they used it in a different way. But the proof is in has no connection in essence with the proof provided first by Braskamp and Lieb. So I thought
Alina,
yes.
sorry to interrupt. This is Emmanuel, but of course, you know, the law concavity was proved by the PD community, by people like Korvar, Lewis. You know, this is the convexity, the concavity of solutions to PDE is a super well-known subject, and you need, you know, this law concavity has been proved and reproved.
No, you're right. You're right in the sense, yes, yes, for a larger class, yes, you're right. For a larger class was proved. Yes, you're right. In fact, there are papers about law concavity of eigenfunctions to solution to semi-linear.
Yes, exactly. So it's not like there was no other proof between Braskamp and Lieb and this fundamental.
No. Okay. So in direct connection with the proof of the bounds of the lower bounds of the fundamental gap, I think for Yao, the first paper, I think for Yao was important to give a new proof, because that was so essential to prove the lower bound that he felt he doesn't want to recall it. So in the appendix, he gave a new proof of the law concavity of U1, which I found amusing, because, as you say, in fact, it was known in some larger group, but he didn't want to give or they didn't want to give a reference to it. So I thought, okay, yeah, you're right. Yeah, actually, that's correct. Yes.
Alina, I just wanted to ask, what operator are you talking about right now?
I'm still talking about it's both the Laplace operator or the Schrödinger operator. So Laplace plus convex positive potential. Either one is the same.
Okay.
Okay. Yeah, with the Dirichlet boundary condition, that's okay if you want. But okay. So let me just go back to the point I wanted to actually make, is that in both cases, the Euclidean case and the spherical case, just law concavity of U1 implies a lower bound, pi squared over d squared. This was not, I mean, already it implied pi squared over 4d squared in the first lower bound ever proved, but then even in the Yu Zhang and Yu Zhang and Ling, they used it just to prove pi squared over d squared. I wouldn't say very easily, but quite directly with a lot of estimates. So the domains that we proved that there is no lower bound for in the hyperbolic case really did not have a law concave first eigenfunction. In fact, this is the thing that we exploited. We exploited the fact that for those domains, given a certain diameter, we can construct domains that are convex, but the first eigenfunction has two maxima. It was symmetric in some sense, if you want, but it has two equal maxima, almost like the union of two balls with some connecting neck, which is not convex in Rn, but basically this is how the first eigenfunction looks like. So however, we also knew that there are domains in H2 whose first eigenfunction is not law concave, but the fundamental gap was bigger than this pi squared over d squared. So it was a little bit puzzling up to what point, if we can find domains that have a law concave first eigenfunction, we can actually prove some lower bound. And so we started to look at the case of balls, because it's the easier case where you can actually calculate the eigenfunctions, even in Hn. And because of symmetry, so because the first eigenfunction is radial. And so also we found our own little proof that it's a law concave that was a little more, even more pleasing, because we wanted to see a little bit in what way is law concave again, and how law concave is it if we can find some bounds on the second derivative with respect to the radial component. And so the proof it's very extremely simple, so I can present it in a few lines. First, you show that U1 is strictly decreasing. The fact that the first eigenfunction is radial will actually change the whole problem into a one-dimensional equation. The boundary values are not anymore Dirichlet on both sides, right? Because the function is the eigenfunction is 0 on the boundary when at R, but not at the origin, right? So we have slightly different boundary conditions, but anyway, it's easy to deal with. And if we multiply the equation by a factor of sinh of t at the power n minus 1, you get immediately that given that u1 prime at 0 was 0, you will also have that it's going to be strictly negative for all time, for all parameters t between 0 and the radius of the ball. So,
Alina, I'm sorry again, but this is for v0, right?
Oh, for v, yes, for v equals 0. Yes, I'm going. Yes, in fact, absolutely. But we'll go a little bit back and forth between. I mean, we are talking about only the Laplace operator with no potential on the hyperbolic space, but somehow at some point you will also see that we're using some results on the Schrodinger operator. But you are right about the fundamental gap on hyperbolic. I'm only talking about the Laplacian with no potential, with zero potential. Okay. So, all right, so then you consider the derivative of the logarithm of the first eigenfunction, and you play about the same game. You try to figure out what is the equation satisfied, and then a very simple argument shows that phi prime 0 is also 0. And then you look at the second derivative of phi, and then you put it into a nice form. So if you would have so what you want to show is that phi prime is negative all the time, but assume that you will have a point. So it's negative when you start at t equals 0. Assume it will not stay that, so you'll have a point at which becomes 0, and then after this it increases. Then you get a contradiction simply just from the form of the equation. So it's not really very difficult to show. And this was enough to show that. Oh, okay. So no. So the first eigenfunction of the geodesic balls are log concave. So our first hope was to show that therefore you can find using this a bound on the fundamental gap, at least on balls. Okay, but this was not the case, because we could prove, and I will show again some idea of the proof. Is very simple, that the fundamental gap for geodesic balls it's of the order, so it's less or equal than a constant depending on dimension, divided by r at the power 3. So as the diameter is like r squared, so you write, okay, so you write r squared times the fundamental gap of the ball will be less than Cn over r. And so when r goes to infinity, you take large balls, this will go to 0. The left hand side will go to 0. So there is no fundamental gap as we know it on hyperbolic balls, even if the first eigenfunction is log concave. Okay, so all right, so then what's next? So the sketch, it's actually, I don't know if I want to go. Okay, I can say a few words. It's a pretty straightforward in the sense of looking at the equation satisfied, again, the radial. So we look at the equation satisfied by the first eigenfunction and first eigenvalue, and then second eigenfunction, second eigenvalue, and we use comparison theorems. Those results, those inequalities that we get like this, it's not one step, but they're like couple of steps put together. They were also known to Savo, and also in dimension 2 to other people, including Gage. So there are many people, actually. In some sense, I omitted to write those down. What I think we got, it's in fact, if I'm not mistaken, is this one that was our own contribution, improving a little bit the concept. Okay, so for the second eigenvalue, we tried to play the same game, but it was a little bit different, the proof, because in the end, so the comparison will not give us something very satisfying. So we ended up just looking at the Rayleigh quotient and estimating the Rayleigh quotient. So here is something that where a potential appears, just to say in connection to Galina's question. So when we studied this, actually we employed quite often a certain change of variables that somehow was not used in the literature, or at least not. I mean, it was used by one of my collaborators on the sphere when she worked on the sphere, but not in general. Namely, that you take this kind of well, she did not use it for sinh, but basically just try to make a change of variables to transform the equation on from an equation where you have all the derivatives, all order derivatives from 2 down, to just a typical well, rather a Schrodinger operator where you have u double prime plus a function u equals lambda u. So we transform the eigenvalue problem into an eigenvalue problem of a Schrodinger operator, but it's one-dimensional, so it's not that that complicated. And we use the Rayleigh quotient, and we use the fact that the spectrum on the Laplace, even with potential function, is discrete, and therefore we can use the same kind of machinery. And so by some analysis of the Rayleigh quotient, we get this upper bound. We get an upper bound of lambda 2, which combined with the lower bound on lambda 1, that one of them before, we end up with this fundamental gap smaller than the constant divided by r cubed, which again shows that there is no fundamental gap for inequality as we know it, as we expected it on the geodesic balls. Okay. Actually, something more interesting came along, though. If we put the two equations in the Schrodinger form for the first eigenfunction, a first eigenvalue, and second eigenfunction, and second eigenvalue, here they're not. I don't distinguish. It's just the equation as two Laplace, as two eigenvalue problems. But the first one is the equation satisfied by the first eigenvalue, and actually the eigenfunction is not u, it's not u bar, it's u, which is u bar is u times a sinh of a certain at a certain power, but the eigenvalues are exactly the same. So the first equation has the first eigenvalue of the Laplace operator on balls, and the second has the second eigenvalue. And so both equations, you look at them as first eigenvalue problem for different Schrodinger operators, but you notice that the Schrodinger operators have a similar form. So you can actually use the technique in Ling to show that to produce out of these two equations, to produce an eigenvalue problem for u2 over u1. So for this u2 bar over u1 bar, where u1 bar is the solution of this with the first eigenvalue problem, and then with the first eigenvalue, and this is, but this is u2 bar with lambda 2, but it's a first eigenvalue problem for the operator itself, for the Schrodinger operator. So you produce an equation for an eigenvalue problem for this, and then that one will be a first eigenvalue problem for phi, and then it will have a first eigenvalue, which will be lambda 2 minus lambda 1 minus, okay, basically is this term. And we know that for any Schrodinger operator with a Dirichlet boundary problem, the first eigenvalue is strictly positive, and so you end up with a lower bound on the eigenvalue of on the difference of eigenvalues of the geodesic balls in terms of a different quantity. So this is more like n-1 over sinh of sinh square of d instead of d squared. Okay, so that was we thought, okay, that's interesting because okay, maybe we can prove something we can prove a different eigenvalue, we can prove a different fundamental gap inequality. It turns out that this is not the case. There is no hope to show that this is true for all convex sets again, because if it will be true, then you will have okay, you can do sinh squared d over d of d over d squared times d squared and lambda 2 minus lambda 1, and this should be greater than a constant depending on n. But for those domains so for every d, we found a domain that has this sufficiently small, less than epsilon. Okay, so sorry, less than epsilon. And then if you take d small enough, this one is going to 0 fast. The numerator is going to 0 faster than d squared. So this will be smaller than epsilon as well. So you can find some domains with small diameter that will violate this inequality. So there is no hope to find different well, this kind of fundamental gap inequality or lower bound for all convex sets or geodesic convex sets. So, and we went back and we said, all right, but maybe let's use the fact that geodesic spheres are horoconvex. So maybe we can look for inequalities of the fundamental gap only within the class of horoscopically convex domains. Roughly this, so the class of h-convex is larger than the class of geodesically convex, and it's easier to see this with smoother domains, because geodesically convex means that the domain has curvature, principal curvature, with certain orientation has all principal curvatures non-negative, and then with horoscopically convex they are they have all principal curvatures greater or equal 1, and in fact for geodesic spheres the principal curvatures are cotangent of the radius of the sphere. So it's clearly greater than 1. Okay, so that's basically summarizing my question. Can we say something about the fundamental gap for horoconvex domains? But again, our main hope was to say perhaps maybe for d squared, but we know it's not for balls. However, we using the balls, we show that this is not particularly true for geodesic balls. It's true in general after a certain value of the diameter, that any kind of horoconvex domain, not only geodesic balls, if you have a diameter greater than 4 logarithm of 2, then you can show that the fundamental gap is smaller than a constant depending on dimension divided by d cube. And again, the same argument shows that this goes to 0. As can be made arbitrarily small if d gets arbitrarily large, and the proof it's kind of easy enough to present it here. So I'll go over the steps. It's so you choose a ball that has the same first eigenvalue as the domain. So you have a horoconvex domain of diameter d, and choose the radius of the ball that satisfies the same eigenvalue as the domain. And then this is again a fact that I mentioned last week. We kind of reproved, not knowing it exists, that for horoconvex domains, the circumradius and the radius are, the difference between them is bounded from above. So if one of them, if the outer radius becomes very large, the inner radius becomes large as well. So therefore, omega. Okay, so we put this aside. We know that we know this, and we look at the inner ball. The inner ball, the radius of the inner ball is bounded below by this function depending on the diameter, and so we know that because it's included in the domain, the ball with that r will have a smaller eigenvalue than the eigenvalue of the big R, and so we have that the radius of omega is greater than the radius of the ball with the same first eigenvalue is greater than that, and so you end up with the with a lower bound on the radius of the ball with the first eigenvalue as the domain. And maybe we can even do a little bit better than this d greater than 4 logarithm of 2. But with that value, it's easier to get it just that the radius is greater than d over 4. And so now we use the isoperimetric type inequality that the fundamental gap of omega is upper bounded by the fundamental gap of the ball with the same first eigenvalue. And then here we have that this is smaller than C of n over R omega cube. And then R omega cube is greater than d over 4. So you end up with C over N d cube. So d squared is definitely not the right function of the diameter to consider in connection with the fundamental gap, no matter what, because horoscopically convex domains are the strongest convex type domains you can have in the hyperbolic, and so this doesn't work. I want to make in the remaining 2-3 minutes make a comment. So that's done. We don't know if sign of sinh of d squared will be valid for all horoscopically convex domains. We know it's not true for all convex domains, geodesically convex, but we don't know if it's true for all horoscopically. We have some feeling that is not true, and so what I'm trying to explain in the remaining minutes, it's something maybe I don't know if it's directly connected, but something that kind of prompted the choice of d squared in Euclidean. The d squared was chosen because d squared times the fundamental gap was invariant under scaling. So we're trying to think, okay, what about the scaling in the hyperbolic? But of course, the equation doesn't have constant coefficients. The eigenvalue problem doesn't have constant coefficients. So this is a little bit harder to deal with. Nonetheless, there are some scaling results. For example, Ben-Gurion Lind proved in the same paper where they showed Payne-Polya-Weinberger conjecture for the hyperbolic. They also show this kind of scaling. Okay, so what is this? This is actually more in the direction of answering a question that was addressed to me about a year ago, maybe by Sergei Bobkov. So when I talked about the non-existence of a fundamental gap in the hyperbolic for geodesically convex, he asked if, okay, I'm working with the hyperbolic with negative curvature -1. What if the negative curvature is very close to 0 or goes to 0? Do we recover the fundamental gap in that way? And the answer turns out to be no, actually, because of this scaling. So here I'm comparing the fundamental gap of convex sets on Hn with negative curvature -1 and on Hn with negative curvature minus k squared, where k goes to 0. So you have the equation in some form, although you can't solve them exactly for all eigenvalues of the balls, and you kind of looking at comparing them. And so what you see here due to this scaling is that if you take the lambda I, you can think of the first eigenvalue. You can take the first eigenvalue of the hyperbolic with curvature -1 over c squared. The 1 over c is the k here. It's gonna scale. It's gonna be like c2 and the radius cr on ball of radius cr is gonna be like c power -2 of lambda 1 with in the hyperbolic space with -1 curvature and radius r. So when you look at this, which is the fundamental gap for balls, geodesic balls, together with this d squared, right? D squared. So the fundamental gap that should be bounded from below by a constant for these geodesic balls in the hyperbolic space with negative curvature -1 over c squared, where c is sufficiently large, you will get that it's smaller than this, and this can be made arbitrarily small. So because we just proved this with constant of n divided by r cube, and r is very large. So that could say that okay, so as long as you have negative curvature, the fundamental gap probably is not true with d squared. And then we looked again at another thing about how is it possible to extend the fundamental gap of sinh squared of r for all sets. So then we were trying to think, okay, what happens? Okay, so what happens when things are very close, with the diameter very close to 0? Because that's basically what we don't believe will make possible that choice of function for the fundamental gap. And the small balls, and I think we believe that this is true for many other sets, maybe horoscopically convex sets. If the diameter goes to 0, because you only prove that the fundamental gap doesn't exist for horoscopically convex, if the diameter goes to infinity, we show that the fundamental gap for balls that are very close to 0 is going to go to it's going to a constant, so it behaves like R2, like Rn. So we believe that it behaves like Rn for horoscopically convex to small diameter too, and therefore this will not kind of reconcile the d squared with the sinh d squared. And so at this point, maybe the problem is still open. Definitely the fundamental gap as was defined with d squared does not work for convex sets in Rn, in Hn, and with either type of negative curvature, -1 or very small. And that's all I had to say.